Welcome to a lesson with Dr. Powell. We're going to look at the geometric interpretation of the dot product and the cross product in 3 dimensions. But first, let's talk about how to find the length of a vector. This is nothing more, so if we have 2, 3, and 5, this is nothing more than a 3-dimensional type version of a Pythagorean theorem. You have this in the x direction, in the y direction, in the z direction, all perpendicular to each other. So to find the length from the origin up to that tip, you simply take the sum of the squares of the lengths of those perpendicular directions and square root it. In the Calculus 2 videos, I discuss this in more depth. So this is the length of a vector. So if this vector is u, then the length of u, I'll notate it like this, using the same symbol for absolute value, distance from origin if you like, is equal to that. So that's how you can find the length. Now you can rescale a vector. If you take this vector, you can rescale it and multiply it by something to make it longer or shorter. In fact, if you were to rescale it by this number right here, which is 4 plus 9, which is 13, plus 25, which is 38, so square root of 38. And if you were to rescale it by multiplying by the reciprocal of that length, 1 over square root of 38, this vector actually, so you take this length and you rescale it by this, I mean, you end up, this actually will have a length of 1. So it'll be a unit vector. Unit vectors are very nice for understanding and thinking about the dot product. Let's see why. All right. So the dot product, let's suppose we have a vector v, and then we have a vector, and let's suppose we have the same vector u. All right. So 2, 3, 5. And let's suppose that this one is something like 5, 2, and maybe -1. All right. So then if I were to take this vector here and rescale it to be a unit vector, then when I take the dot product of v and the rescaled vector, which is the unit vector, the dot product, I'm actually going to get a number out. Remember, I don't get a vector, I get a number. And that vector is precisely this length from here to here. If I take a perpendicular line going up like this between these two, well, and this is in 3 dimensions, and at least it's on the plane that has u and v in it, and so we might call that orthogonal. Orthogonal is another word for perpendicular when we're in 3 dimensions. So this length right here is going to be the dot product of this unit vector, which I can notate like this: u over absolute value of u multiplied or dotted with v. So that dot product is going to be that length. We could do that pretty quickly. Let's see how we can do that. So if we take, and actually for the dot product, because we're ending up getting something real, order doesn't matter for dot product. We get the same thing. It only matters for the cross product. So let's look at that. If we have 5, 2, -1, that's v, and we take u over u bar, or over u, but absolute value of u, and so let's just rewrite it like this with this scaled out. We could multiply this into the components, but let's just keep it out for the dot product calculation. It makes it simpler. 2, 3, 5. Then we simply just take the dot product, add, and then multiply by this, we'll call it a scalar because it rescales the vector, but it's just a number. So 5 times 2 is 10, plus 2 times 3 is 6, plus -1 times 5, that's -5. and multiplying it by 1 over square root of 38. And so we get 10 plus 6 minus 5. That would be 11. So we get 11 over the square root of 38 is actually equal to that projection from this vector onto that one. And so that is kind of how to think about the dot product. It works really well with unit vectors. Now, also along that line, what if we have two vectors and we dot them together and we end up getting 0 projection length? Well, and let's suppose that neither of these are a unit vector, but that's okay, because if you rescale both sides of this equation, notice this is a number, that's a number, by anything like this, wouldn't we still get 0 on this side? Meaning that the projection would be 0. So dot product 0 actually means projection 0. But it's just easier to take a dot product than do a projection because you're not dividing by anything. So this is a common thing that we use. Dot product being equal to 0 means, if and only if even, projection length is 0. And that's great because that means that the two vectors themselves are orthogonal to each other. So dot product and orthogonal or perpendicular are equivalent or orthogonal. So computationally, dot product equaling 0 is used all the time synonymously with orthogonality or making sure that something is perpendicular. So that's a great thing to use for dot product. Dot product is also very useful when you're thinking about angles, V and U, and you want to compute the angle between them. Well, since we made a right triangle and we know what this length is using a dot product with rescaling U to a unit length, so this would be V dot product with U over that, the absolute value of U. So you know this. And if you were to take the length of V, we have a little triangle, and we can use the fact that the cosine of the angle is equal to adjacent over hypotenuse in order to find the angle. So that's also a very nice use of the dot product between two different vectors. Okay, let's think about the cross product now. Okay, so what about the cross product and how to interpret that? Well, when we do a rotation, a four-dimensional rotation, when we multiply by quaternions here, in the sense that's required in order to rotate one of the vectors to the real axis, which we don't see, what ends up happening is we end up getting, let's take a look at, so we were looking at the projection length. Let's suppose that we had a unit vector as well, so that it really was a rotation. Then what we end up getting is the dot product was this, the projection onto the real part, and the cross product is actually imaginary. You see it completely, and it is a vector. And notice it has no real component, it's just imaginary. Now, this vector right here, how to think about it? Well, it's going to be orthogonal to the real part, and it's going to be imaginary. But this picture doesn't tell us everything. The operations I, j, and k, when you multiply by them, actually always produce something that's orthogonal. Any sum of them also produces something that's orthogonal. In other words, when you just simply multiply by imaginary quaternions to themselves, you always get something orthogonal. It's kind of nifty. So the cross product, kind of the basic idea that we always use, it doesn't matter what they are. If you always take a cross product, you always get something that is orthogonal to the two vectors you started with. So if we were to take a vector u and a vector v, and we take a cross product of the two, we end up getting something that's completely orthogonal. Now, which direction should it be located? Well, quaternion multiplication, what we can do is we can actually let's just multiply our picture or kind of rewire it so the u is actually pointing in the x direction only, to kind of see where this cross product is going to be pointed. So in the x direction, and then the v will be coming out, and let's suppose that the v is coming out this way, but let's only take the component of v that's perpendicular, because the component that's not, the only thing that matters, anything that's not perpendicular in the component of v is going to be alongside of it, and it's going to feed in to the dot product or that projection. So really all that's required is thinking of the component that's perpendicular. That's going to be headed in the y direction then. And you notice that I times j in our little thing always went up k to positive z. Well, that tells us exactly what direction it goes. If you draw on a piece of paper and you have u and v, and u, and to get from u to v is counterclockwise, just like it's counterclockwise here to get from x to y, then the cross product is always pointed out of the paper or up. And then it's always pointed into the paper if it's opposite. So in this picture, u cross v should be orthogonal, pointed out. But if we were to take v cross u, then that would be pointed in. And so that is a nice intuitive sense for what cross product means. We talked about computationally how to compute the cross product in the last video. And one more thought on the cross product is if you happen to be a unit vector and kind of, with this rotation deal, but then we put the length of u back in, what ends up happening is we end up getting the height of a parallelogram. That's what we get when when this is a unit vector, but then when it's not, then we multiply by the base, which ends up giving us the area of a parallelogram, meaning that the actual length of the vector u cross v is the area of the parallelogram formed between the vectors v and the vector u. So that is a very brief synopsis of the geometric intuition that we can get from the dot product and the cross product. Thanks for watching.